Today we'll get an introduction to what vector fields are. So they're a pretty big deal as far as they're the last new kind of function that we're going to study in multivariable calculus. They're an example of a vector valued function of several variables. So a vector field is going to be nominally just a function from our vector space, our xy plane, for example, if we have a function of two variables, and its output is also a vector in that same space. So that's how a vector field works. It takes in, you might think of it as it takes in a point in Euclidean space as its input, and it spits out a direction vector in that same Euclidean space as its output. So a vector field in the xy plane, for example, would have x and y as its input variables, and it would spit out an xy plane vector as its output. So first thing we're going to do is just kind of get used to how to think about what vector fields are, how to visualize what a vector field looks like, and some of the sort of other entities and objects that we can relate vector fields to. Today we're going to spend a little bit of time looking at what are called the integral curves of a vector field. These are just going to be parameterized curves that follow the arrows of that vector field. In other words, the tangent vectors of those parameterized curves are exactly equal to the values of the vector field as we move along that curve. So the vector field just sort of points in the same direction and with the same velocity as our parameterized curve does. We call those the integral curves of a vector field. We're not going to spend any time in our course actually solving to find the integral curves of a vector field. That's really a topic that belongs to a differential equations course, and in particular kind of a differential equations course that handles sort of multi-dimensional diffeaqs, which is not, there aren't that many introductory courses in differential equations that do that. So that's, we're not going to do that analytically. We're going to use it as a graphical tool, and we have another suite of online graphical visualization tools that we'll use to kind of get our hands around that for today. And then we'll shift gears toward the end of today and talk about one of the most important sources for where we get vector fields from, and that is from taking the gradient of a scalar valued differentiable function. So the gradient vector that we computed back in chapter 10, right, when we were first introduced to the gradient, we thought about it as a vector back then, but what we didn't dwell on is the fact that that gradient vector also typically depends on x and y, and x and y and z, or however many variables your original function has. Your gradient vector is going to depend on those variables as well. And so the gradient vector is itself a function of those same several variables that our original function was a function of, but also its output are vectors in that same space as where our inputs came from. So the gradient is actually a vector field. It's more than just a vector. It's a vector field because it can give us a different vector potentially at different points in our space. And so we're going to dwell today on when we get a vector field from taking the gradient of a scalar valued function, what kind of special properties do those vector fields have that might set them apart from other vector fields that we just might kind of write down formulas for. So when we have a vector field that is the gradient of some scalar valued function, those vector fields have special properties that we want to begin to sort of scratch the surface of those properties today. What we have to look forward to as we move through the rest of this chapter is we're going to be able to look at both some topics in the differential calculus of vector fields and also in the integral calculus of vector fields. So now that we have an understanding after today about what vector fields are, we're going to be able to discuss derivatives related to vector fields and integrals related to vector fields. One of the interesting things about vector fields is that it's actually a little bit more natural, I think, in the beginning to think about integration first. So the integral calculus of vector fields is actually the first calculus that we're going to meet. When we talk about the ideas of what are called line integrals or path integrals, that's coming in the next 3 sections after this one. And then as we build on that a little bit more, we're going to discover that the differential calculus, so the kinds of derivatives that we can associate with vector fields, are actually related to the ideas of integrals that we develop for vector fields. So we're going to talk about 2 important quantities we can relate to a vector field. One of them is called circulation, which is kind of a measurement of how much a vector field is kind of rotating at a certain point. So how much might it spin a little toy boat if we put it in the vector field and let it flow. So circulation is one measurement that we're going to get at on a total basis using a line integral, and then on a local basis using what's called, one of the derivatives of a vector field is called the curl of a vector field. So the curl is going to be a local infinitesimal measurement of circulation, whereas a line integral around a closed path is going to give us a total net measurement of circulation. But then there's a second type of derivative for vector fields that, roughly speaking, is going to measure how much that vector field is either increasing or decreasing the area or volume of a region as it flows along the vector field. And that's going to be related to an infinitesimal quantity called the divergence of a vector field. So those are the two types of derivatives that we're going to study for vector fields, curls and divergences. And each one of those is related to a type of line integral or path integral that we can compute. And where the whole thing reaches its apotheosis is in a theorem that is behind my head here. So let me move my head out of the way. There are these really important theorems that are called the Stokes Theorems that give us a relationship between the integral and the differential types of measurement of these quantities. So the circulation and the divergence, circulation and the flux of a vector field are total quantities that we can measure by integrals, but they're also infinitesimal quantities that we can measure by derivatives. And the Stokes theorems are the relationship between those. So they're basically just juiced up versions of the fundamental theorem of calculus. The fundamental theorem of calculus that you learn in Calc 1 tells us that derivatives and integrals are actually not that different from one another, right? That in order to define an integral, we can use the opposite of a derivative, right? And vice versa, that the derivative of an integral quantity sort of cancels each other out, right? Derivatives and antiderivatives have that relationship. And so the Stokes theorems for us, when we do vector field analysis, are going to be just souped up versions of the fundamental theorem of calculus that tell us that if we want to measure the total circulation of a vector field, for example, that we can do that by measuring the infinitesimal circulation, which is a derivative, and then adding up those derivatives over the course of some surface or some region, right? And so that adding up process is an integration process, and since that integral is going to happen in 2-space or 3-space, yes, we're going to be doing double and triple integrals in the process. So what's really nice about this as a last chapter, a last act in our play that is multivariable calculus, is it really pulls all of the threads of what we've been studying this semester together. Because when you do vector field analysis, you end up doing, as I say, multiple integrals. You end up getting vector fields from taking gradients of things, and then the gradients can tell us something about those scalar value functions. As we're going to see, for example, today, the gradient vector field of a function of several variables has information in it about the local maximum and minimum points of that function. Because after all, it is the gradient that we find if we want to figure out where are the local maximum and minimum points of a function. And so all those threads are going to get tied together in this last chapter on vector fields. And that's why, for us, I felt like spending the lion's share of our second half of the semester on this chapter is really time well spent. Because it's not like we're leaving any of our previous topics behind. They're going to keep coming back and haunting / helping us along the way.